11.2 solubility curves. Starting off with saturation. And we talked about solutions last week. Put some water into a beaker, that's your solvent. Put some salt into it, it dissolves, you have a solution. And the salt would be your solute. Well, here's the concept today. Solvents, generally water, can only dissolve so much solute. You have to think about that. You got a beaker of water. You can't just dump unlimited salt in there. Eventually, you're going to reach this maximum level that the water can dissolve.
Well, I reach maximum level where the water can dissolve and where no more salt will dissolve.
Right, where no more salt will dissolve. You might still be able to put some salt into the water, but it's not going to dissolve. It just falls out to the bottom like you see salt, and you're like, well, it's going in there, and I still see it, which is unusual, right? We know when we put salt in water, it dissolves. Well, at a certain point, you'd have so much salt in the water that no more could dissolve. And so even if you poured more in, it would just start to pile up on the bottom like a solid. So once you've reached the maximum amount of solute that you can put into a solvent and be dissolved, we then say that that solution is saturated. It's a Greek word, it means full. So your water is full of solute. You cannot dissolve, you can put more in, but you can't dissolve any more salt. It is saturated. Up until this point, so as long as you're adding salt and it is dissolving, as long as you haven't reached that saturation point, we say that the solution is unsaturated or not full, unfull. And that brings us to the main point we're looking at today. Solubility curves. So this is going to be a graph, mostly with curves on it. You'll notice the first one we draw won't be a curve, but most of them are going to be curves. And so that's why this is called solubility curves. All right, so like I said, it's going to be a graph. Our X and our Y axis here. And this axis is super, super, super important. Watch how I'm going to label this. So that part there is super, super important. What this axis is showing you, this is a measurement of how much salt, how much solute in grams that you can dissolve per 100 milliliters of water. So that's really important. We're looking at how much salt you can dissolve per 100 milliliters of water. Why is that important? Well, sometimes a question will give you 50 milliliters of water. And you have to recognize that. And you have to say, well, it's only 50 milliliters of water. That's only half the amount of water. So we can only dissolve half the amount of salt. Or sometimes they might give you 200 milliliters of water. And pretty much the same story, except this time we're going to double the amount of salt. So if you could dissolve 40 grams in 100 milliliters, if I gave you 200 milliliters, you'd be able to dissolve 80 grams. So you got to kind of watch how much water you have. And sometimes you might have to do multiplication or division to figure out, hey, based on what you have, here's how much salt you can dissolve. On the x-axis, then, we have our temperature of solution in degrees Celsius. Why is that important? Well, as you guys will see, generally, you can dissolve more salt the higher the temperature. So as you warm up water, you can actually dissolve more grams of solute per 100 milliliters. So that's why we look at the temperature versus how much salt we can dissolve. Good so far? So real quick, wanted to point out, this is just kind of a freehand drawing of what these graphs will look like. On your homework tonight, make sure you guys use the real one that I give you. That one will be a lot more precise than my, my freehand drawing here. Does anybody notice a difference between what I have underlined here and what I have underlined up here? Perfect. Yep. For you guys at home, perhaps you didn't hear, One is grams, one is milliliters. Don't let that disrupt you. A nice little trick for water. We can use this for water. Sometimes it's really, really valuable. It's a really important tool. But the density of water is 1 gram per milliliter. That means 100 grams of water is the same as 100 milliliters of water. So don't let it throw you off if sometimes it says milliliters and sometimes it says grams. For water, they're the same. Right, exactly. Other substances have different densities, so it doesn't work for other substances. But water is really cool that mass and volume are going to be the same. That's your question? Yeah, that's a good one. I'm glad you recognize that. Yep, good. Awesome. So yeah, don't be confused by grams and milliliters. They are the same. So anything on the line or above it is considered saturated. So an example type question you guys will see in your homework tonight that I would ask. Something's going on over there. All right, so an example type question you guys will probably have on your homework is like using this curve, using this graph, describe a solution that has 100 grams table salt, NaCl, in 100 milliliters of H2O at 40 degrees Celsius. So how we use our table here, how we use our graph, is I would say, okay, lucky for us, working with 100 milliliters, right? So we're not going to have to do anything with our answer. It's going to be exactly what it is because we have 100 milliliters. All right, 40 degrees Celsius. Here's our 40 degrees Celsius. We follow that up until we hit the line. Follow that over. Now there's going to be some guesswork in this. These graphs are not terribly precise. I mean, they can be. I could find one, but I don't have one that's terribly precise. So there's going to be some guesswork. We know it's between 25 and 50. Well, let's go with 35. I'm okay with that. If you said 40, I'd be fine with it. If you guys said 45, I'd be okay with it. Just, somewhere between 25 and 50, preferably closer to the middle. 35 works for me. So how we'd answer this question is, so remember, we put 100 grams in. If 35 of them dissolve, that means 65 grams are just going to fall to the bottom of our solution. We're just going to have a beaker of salt water. It's going to be mostly solution, but then you're also going to have 65 grams of salt sitting on the bottom of your beaker. It will have fallen out. So everybody sees where we got these two values from? finish that. I'll go check on her. Doing all right. All right, another similar type question. Definitely see this type on your homework tonight. How much NaCl could... I'll be right back. She's putting the thing like papers up in her on their wall really high up, so she's like reaching and taking the stapler and going wham. She's okay. All right, so another type of question. How much NaCl could we dissolve in? Catch it, catch it, catch it. Here's the trick. Only 50 grams. You guys notice that? At 20 degrees Celsius. All right, so we go up, we find our graph. Here's our 20 degrees. Follow that up, hit the line. That's our maximum amount. Follow that over. And again, there might be a little bit of guesswork here. If we said this first one is 35, let's call this one 30. You said 32. If you said 28, I'm okay with it. I'm perfectly all right with it. Somewhere in that range is going to be just fine. Let's call that 30 grams. But then here's the thing. We need to divide 2. Divide it by 2. Why 2? Well, because we only have 50 grams. And this tells me how much I can dissolve at 100 grams. So in only 50 grams, I'll be able to dissolve 15 grams of salt. Only half the amount. If I only have half the water, I can only dissolve half the amount. Make sense?
Yeah.
What's that?
So 15 grams is how much is going to dissolve.
Right, so they're asking what is the maximum amount. So in a question like this, they're asking what is the maximum amount you can dissolve. So we look at our graph, we go up to the line. The line shows us where we're saturated at, where we're full. So we can dissolve 15 grams, well, we can dissolve 30 grams per 100 milliliters. So that would be our answer. Then we divide it by 2 though, because we only have 50 grams, 50 milliliters of water. So the maximum amount of salt we could dissolve is 15 grams. Again, generally, as your temperature goes up, it means more salt can be dissolved. Warmer water can dissolve more salt. So another type of question, can it utilizing that whole you can dissolve more at higher temperatures? This question is stating you have a saturated 100 milliliter solution. So that's always nice when we have the 100 milliliters because then we don't have to think about doubling it or halving it or whatever. So we have a saturated 100 milliliter solution of NaCl at 20 degrees Celsius. How much more salt could we add if you bring the temperature up to 100 degrees Celsius? Okay, so this question kind of has two parts. First part, how much can we dissolve at 20 degrees? Well, I think we've already done that one. I think we said 30 grams. I'm good saying that. How much can we dissolve at 100 degrees? So we're going to follow that up. There's the dot. Call it 48. Sure, I'm good with that. So 30 grams and 48 grams. And we'll be able to dissolve 18 more grams at the higher temperature. Any questions? NaCl is kind of boring. It's just kind of a slow sloping line, kind of a boring line. But most salts aren't that way. So turning back to this page, for example, and on your homework, most of the time you guys, when you see a solubility curve, you see a whole bunch of lines, you see a whole bunch of different salts. So another one is KNO3, which looks like that. Potassium nitrate has a curve like that. Now you can see why they're called a curve, right? Sodium chloride is really kind of boring, but a lot of them have this exponential growth almost. Like they really, really go start going fast as you get to a higher temperature. Potassium nitrate is one of them. It increases a lot more dramatically.
So,
That's what,
um, so for like what we're doing on the homework is all the questions gonna ask like, um, is it gonna have like H2O in it, or is it gonna be like different liquids?
no, you're always going to work with H2O.
Oh,
Yeah,
okay.
water's pretty much always our solvent.
Okay.
That's an interesting question. I suppose there could be a different solubility curve for different substances, but no, yeah, we're always going to work with water.
Okay. Yeah, I was just wondering because you said like how water and like the grams of water and mLs of
The
water.
density
Like,
of water, yeah.
yeah.
Yep, no,
Oh,
water's really the only substance that can do that.
okay.
All right, every once in a while, you guys will see a downward slope. So salts generally increase as the temperature increases, but sometimes you see a downward one. Molecules, and hey, just kind of one of those heads up, molecules are covalently bonded molecules. So covalent bonds, like H2O, it's a covalent bond. Carbon dioxide, CO2, it's a covalent bond. These guys decrease in solubility as the temperature increases. So they're kind of the opposite of ionics. And guys, you're probably already aware of this, whether you realize it or not, because you probably have something at home that does this.
Oh, doesn't candle wax do that? I know you like candle wax. How does it do?
I've never tried to dissolve anything in candle wax. But what I was referring to is dissolved in water. Covalents like CO2 go downward. So if you ever have one of these downward curves, it's a covalent. It's a covalent molecule. What I was referring to is soda. If you guys have any pop at home, soda pop, Coke, whatever you want to call it, it's got the carbonation in it. Guess what carbonation is? Carbonation is carbon dioxide. Where do you keep your soda at home? In the refrigerator. Why is that? Well, because lower temperatures, you can keep more carbonation in the soda. If you let your soda get warm, you lose a lot of the carbonation and eventually it'll go flat. Lose all the gas in there and you don't have good soda anymore. So that's why we refrigerate our carbonated beverages, because you can keep more gas in the liquid. You keep more of it dissolved. All right, a couple more examples here. I'll set you guys loose. bringing back in what we did last week and applying that. Aha! All right, so to set up this problem here, what is its molarity? What is its molarity? Okay. Question mark, moles over liters. We're looking for molarity. Whenever you guys see molarity or big M, you need to think moles over liters. It's tough to work mathematically with just big M, but moles over liters, we can work with. All right, is equal to, well, I know I've got 200 milliliters, and it's going to be pretty easy to go milliliters to liters. That's a pretty easy conversion. On top, I'm either going to need moles or grams. If you guys get grams of a substance, we should be able to get to moles. We know how to do that. Well, we don't have either, but working with our solubility curve, we can figure mass out. 80 degrees Celsius, KNO3, 200 milliliters. Let's go take a look. Here's your KNO3, 80 degrees Celsius, follow it up right in there. Since we called this 30 earlier, it's got to be a little lower than 30. Let's say 28. So we have 28 grams of KNO3. Or do we? Do we have 28 grams of KNO3?
No.
Why not?
Because it's more than 100.
Awesome. Perfect. Yep. Notice the trick. We've got 200 milliliters. We could dissolve 28 grams in 100 milliliters. This is twice that. So we need to double it. All right. You guys want to do the easy step first or the hard step first? Not that either one's particularly hard, but I think one's get a little bit more work than the other one. One vote for hard. Everybody's all right with that? All right, cool. I would think that the harder step, not that it's hard, but just requires a little more work, is going grams. Moles. And the reason why it requires a little more work is we need to come up with a molar mass. Potassium here with KNO3, so there's potassium. Nitrogen, there's nitrogen. And 3 oxygens. There's oxygen. I got to put 3 of them. Add all these guys up. Let's see here, 39.0983 plus 14.00674 plus 3 parentheses, 15.9994 close parentheses, press the equal button. (101.10324 grams per mole). We go 4 past the decimal, 5 past the decimal, 4 past the decimal. So underline that 4, he's not significant. Bring that number up here. Cool. All right, we've gone grams to moles. Now we do the easy step, or at least what I would consider the easy step. We just got to memorize that there are 1,000 milliliters per liter. Got to make sure you put milliliters on the top. That way it cancels out. It's on the bottom here, so you got to make sure it's on the top. Also, that gets liters on the bottom, which is exactly what we want. We want liters on the bottom. So, it does both things we needed to do. For those of you who like to cross out things, grams is gone, milliliters is gone, and we're left. The only two units we have is moles over liters. It's exactly what we want. Hey, take out your calculators. Take out your calculators. Plug this in. See what answer you get. Give you guys a minute. People at home, do this. Get your calculators out. Plug this in. See what answer you get. I'm having you do this because in grading your homework, guys, most of you guys are setting up your problems perfectly. But then you're making a mistake on your answer, which means you're probably not entering it into your calculator correctly. And how annoying is that? You're doing all this perfect work and you're not getting the right answer because you're not entering it into your calculator correctly. That's annoying. So do me a favor, get out your calculators, solve for this. Just keep it on your calculator. You can see what the number is. Then I'm going to plug it in. You guys can see if you get the same number as me. And some of you may not, because I think you're doing something. I noticed on your homework, I think you're doing something that is throwing your numbers off. All right, so I'm going to plug it in. I got 2 parentheses, 28, close parentheses, divided by 200. Here's the big step right here. I think a lot of you guys see these two numbers together and you multiply them. Don't. I think a lot of you guys are doing that. In fact, I know a lot of you guys are doing that. I see the answer you're putting down. Your work is perfect. You're getting the wrong answer. Don't hit the time symbol. Get divided by 200. I'm going to say divided by 101.10324 times, because it's on the top, 1,000. $2.769. Significant digits are going to be top. We're reading that graph. We're getting most of our numbers off that graph. So I'll just call this 2.77 molar. Guys, I'm telling you, a lot of you are multiplying this number here. Because you see a number like this, 200, and it's right next to you. You're like, wow, 200 times 101. It's throwing off your calculation. You've got everything set up perfectly, and you're ending up with a much larger number. If you ever have a number on the bottom, hit divided by. Hit divided by. Don't care if it's divided by, that's fine. It's supposed to be divided by. So don't multiply these two numbers, which again, I think a lot of you, don't think, I know a lot of you guys is doing. Don't hit times, hit divided by. Everybody okay with that? Hey, remember last week when we had that question that said 6 molar, 6M? And I was like, man, that is a really concentrated solution. Well, yeah, I mean, yeah, look at this. That's a saturated solution. The most concentrated solution we can make is 2.77 molar. That is a saturated solution right there. So yeah, if you ever have something that's like 6 molar, man, watch out. That is some strong stuff. What's that? Well, it probably depends what the substance is. If it's salt water, no. So depends what the material is. But yeah, for this one, 6 molar would be pretty concentrated. All right, one more example here. Again, similar type question as to what we worked on last week. We're looking for a percent mass to volume, 2-liter saturated solution at 20 degrees Celsius. What's it saturated with? Well, we're working with soda, and the molecule in soda is carbon dioxide. All right, so we're looking for the mass to volume. So start this one off, question mark, grams of solute over milliliters solution. We need grams of solute over milliliters of solution. I've got 2 liters of solution. I can pretty easily go 2 liters to milliliters. Liters to milliliters, pretty easy to do. But we're going to have to figure out the mass. We're at 20 degrees Celsius. We're working with CO2. So let's go take a look. All right, 20 degrees. Here's our line for CO2. Boy, that's right on the other line. Let's call that 30 grams. Pretty much right where that other dot is. Let's call that 30 grams. That's fine with me. Here's the thing. Got to do a little math here. That's 30 grams per 100 milliliters. How much do we have? Oh, we got 2 liters. Yeah, think of 2 liters as like 2,000. So how many 100s are in 2,000?
Oh, I didn't say that right.
You got one too many zeros. Yeah. 20. 20, right? You can think of it as there being 10 100s and 1,000. So that means there's 20 per 2,000. So we got to multiply this number here by 20 because we've got 30 grams per 100 milliliters, but we have 2,000 total milliliters. We have a 2 liter, right? So hey, look at that. We've already got grams on top. We already have our grams on top. Awesome. Wonderful. The only thing we need to do is get milliliters on the bottom. Since I've got liters here, I want liters there. 1,000 milliliters in a liter. Now we just need to crunch the numbers. Again, since it's on bottom, hit the divided by sign. Don't do 20 times 30 divided by 2 times 1,000. You get the wrong answer. You got to do 20 times 30 divided by 2 divided by 1,000. Last thing then, don't forget, multiply by 100%. And we're getting a 30% solution, carbon dioxide to water in our soda. Questions? People on Zoom, any questions?